So we're now going to define a second dimensionless group, which we call the fin efficiency. The fin efficiency we define as the heat transfer through the fin divided by the heat transfer if the entire fin were at the base temperature, T sub B. We define this ratio as eta sub F. What this dimensionless group is telling us is how much heat is transferred through our actual fin relative to if the entire fin could be held at that same temperature, if it were a perfectly conductive fin that could be held at the base temperature. So if we plug in, we get Q sub F in the numerator and H times A sub F, which is the area of the entire fin, its whole surface area, times beta sub B. If we plug in for Q sub F and we do some math, we'll find that eta sub F equals the hyperbolic tangent of m times L divided by m times L. So we can look at this solution first in its limits. As ml approaches 0, the numerator and denominator are both 0, so we have to apply L'Hopital's rule. If we do this, we find that the fin efficiency approaches 1. This means that for a fin which is relatively short, its heat transfer is a lot like holding the entire fin at T sub B, and hence the fin efficiency is 1. We can also consider a fin which is really long. This is sending m times L to infinity. And in this limit, the fin efficiency goes to 0. The fin is now, for a very long fin, nowhere near the base temperature. So the fin has a relatively low efficiency relative to the case where the entire fin is at T sub B. We can plot this just to help bring this to life. We've done this on a log-log plot, placing log of eta sub F on the y-axis and log of ml on the x-axis. For small values of ml, as we mentioned a moment ago, the function saturates at 1, whereas for very long fins, the efficiency goes to 0. Because this is a log-log plot, the function's decline to 0 is not what we typically expect on non-log-log axes.